Okay, welcome back for the last talk of today, and I'm delighted to introduce my colleague Qin Li, who's going to talk about RCD and LMC, and that's randomized coordinate descent and Langevin Monte Carlo. Okay, Qin, take it away.
Thank you. Thank you very much for having me here. It's really my great pleasure to have this opportunity to demonstrate the collection of our work during the past 2 years. I would like to talk about random coordinate descent and LMC, Langevin Monte Carlo. This is just to incorporate random coordinate descent as an optimization algorithm into Langevin Monte Carlo as a sampling method. So random coordinate descent as an optimization method, it improves over gradient descent in the numerical efficiency. And we would like to see when you incorporate the same strategy, this concept into LMC, do you see the same improvement? So during the last 2 years or so, we have experienced a lot of upturns and downturns. So given the speed of the development of this field and the density of smart people in this area, it feels like roller coasting to me. But finally, at least today, I think we can say that we have the full recipe of the understanding. So it's a review type talk where I'm going to give you a collection different ways to incorporate random coordinate descent into LMC, and we're going to discuss the pros and cons for different methods. Okay, so this is a joint work with my student Jian. He gave a talk yesterday already, and I think he impressed some of you, and he's on the job market, he's looking for a postdoc position. Jian has been helping out a lot, and a special thanks to Steve, who introduced us to RCD, this concept. Okay, so the core question, the core theme of the talk is how do you sample from a distribution function? That's also the core theme of this whole workshop. And there are many aspects to look at this problem, and our perspective is to enhance the numerical efficiency when the dimension is high. So the framework that we have, we are going to incorporate random coordinate descent into Langevin Monte Carlo. So in some sense, random coordinate descent is our key to the problem. So let's quickly go over the concepts. Langevin Monte Carlo, it can be regarded as a discrete version of Langevin dynamics. That is to say that you write down the stochastic differential equation, and the stochastic differential equation, the invariant measure is your target distribution. So develop these terms very strategically. You exponentially converge to the invariant measure. So Langevin Monte Carlo is a discrete version of it. So ideally, it exponentially converges to the invariant measure as well up to the discretization error. At some point, your discretization error dominant, and that is a term that tells you how your algorithm depends on kappa, the conditioning of the problem, epsilon, the accuracy, and d, the dimensionality of the problem. So usually it's algebraical. And our problem is whichever Langevin Monte Carlo that you use, it usually requires a full gradient per each iteration. And we think that's a lot of cost. So let's take a look. Overdamped Langevin Monte Carlo is the method developed from the overdamped Langevin dynamics. So this is your stochastic differential equation. You have two terms balancing each other. One term drives you down to the equilibrium, to the minimum point, and the other term gives you the fluctuation. And when you do the discretization, you march forward by descending along the gradient, and on top of that, you add a Brownian motion term. You add a Gaussian random variable. And we know that for the convergence, the number of iteration you have to pay is d to some power over epsilon to some power. And this power can improve if you have better regularities of f. Okay, so our question is, over here in each iteration, you march from one sample to another sample, you have to compute the full gradient. The gradient has d component, you have d, those many partial derivatives that automatically add you another d to the cost. And we think d squared is too much. We would like to reduce that. So the same story is for the underdamped Langevin Monte Carlo. The underdamped Langevin Monte Carlo is derived from underdamped Langevin dynamics. And the way we look at the underdamped Langevin Monte Carlo is the spring system. So you have x dot equals to v, and v dot equals the friction term and the potential term. When the potential term is not x squared, you have an extended version, and this Brownian motion basically gives you some fluctuation on the velocity, on the acceleration. So you oscillate, and eventually you comes down to the equilibrium. So on top of this underdamped Langevin dynamics, we have the underdamped Langevin Monte Carlo method, conditioned on the previous iteration solution xm and vm. You march forward for xm plus 1, vm plus 1. Then this the new iteration solution is a Gaussian random variable with explicitly computable mean and explicitly computable covariance matrix. So you draw your sample from this Gaussian. Also, for epsilon accuracy, the number of iteration you have to pay algebraically depend on d and epsilon. And the same story that in each iteration, you have to compute the full gradient. And we think that's too much. It automatically adds you d, those many costs. So we would like to remove that. So that's a summary. Both overdamped and underdamped Langevin Monte Carlo has a pretty high dependence on the d when you think about the cost. So we usually view the Bayesian inference or Bayesian sampling method as an extended version of the optimization. You can either view it as an optimization over the function space, or you can view the algorithm is to optimization algorithm adding the Brownian motion term. So whenever we encounter some difficulty in the Bayesian sampling, we go back to optimization and ask, have we encountered similar difficulties, and what are the strategies that we have over there? So we took out our toolbox and asked, what are the algorithms over there that help us to reduce the cost? The cost comes from the dimensionality when you compute the gradient. So that's where we come up with the random coordinate descent. The random coordinate descent, the story goes back to the classical algorithm, the gradient descent. The gradient descent says you want to compute the minimum of a function, then you descend along the gradient. It can be viewed as a discrete version of this ODE. The same story, in each iteration, you have to compute the full gradient, and each gradient has d component. You have to compute d partial derivative, and that's a lot of cost. So the random coordinate descent is simply to say, how about in each iteration, I look at my d, those many coordinates, and I just select one and update only that one. I keep everybody else untouched. So I only compute one partial derivative and remove or set the other partial derivative to be 0. So of course, immediately you'll see that the cost is saved per iteration from d dimension to 1 dimension. So per iteration, the cost is reduced by d already. However, it is not immediate that random coordinate descent is eventually going to win. So in order to descend, in order to find the minimizer, eventually every coordinate needs to be updated. So if in each iteration, you only update one coordinate, you have to pay d those many iterations to get everybody updated. So although in each iteration you say by default, you have to iterate more times. So it's not immediate that RCD eventually is going to win. So there are some dedicated analysis over there, and eventually we do say that the random coordinate descent wins in some sense. So the cost of the gradient descent, the cost of the gradient, the number of iterations you have to compute is L over mu, with mu being the convexity coefficient and L being the Lipschitz constant for the gradient. And on top of that, because in each iteration you compute d those many partial derivatives, the cost is this much. So that's a very classical result. And random coordinate descent says the cost is almost identical. You still have the d dependence, you still have the mu dependence, but you replace L by L max. What is L max? So you write down H as your Hessian. The mu as a convexity is a lower bound. L as a Lipschitz constant is the upper bound. And L max is simply the biggest entry along the diagonal. The biggest entry along the diagonal of the Hessian, that basically indicates I'm looking at the stiffness of that particular coordinate in the objective function, and I'm picking the biggest stiffness. So L max is proved. It can be demonstrated that L max is always smaller than L. That is basically saying the random coordinate descent is always going to be cheaper than the gradient descent. And in some situations, L can be as big as D times L max. So if you plug it in, you basically have D square L max. That basically means in these situations, the gradient descent is going to be D folded more expensive than the random coordinate descent. So in some situations, you can find that random coordinate descent saves by a lot. And we should emphasize that, well, both these inequalities are sharp. Yes, please.
Randomly, would you get the same feeling of the error if you just went through the coordinates one by one?
Oh yeah, there are algorithms like that. Yeah.
So is there any difference in kind of in performance?
We didn't check that, but
Actually, I was just asking about the theorem.
yeah. Oh yeah. Yes. Put it up here. Oh. Oh, yes. Thank you. For optimization, I actually don't know.
If you did not choose the coordinates randomly, but just went one by one, right? In order, right? You know, the first, second, third, right?
There is a slight problem. The coordinates get chosen not completely random. Each coordinate gets chosen with different probability. It depends on the stiffness of that coordinate.
Yeah, the answer is no. There are kind of worst case examples where scrolling through the coordinates in order is worse. But in practice, they're usually pretty much the same.
Yes.
So for the results that are shown, is it with high probability or because the algorithm is randomized? So how do I interpret the results?
Expectation.
Oh, okay, thank you.
Okay, should we continue? Right, so we were saying that both inequalities are sharp. That means you can find examples that make this both inequality holds true. So in the first case, that is when the Hessian is a diagonal matrix. The diagonal matrix basically means each coordinate, it depends on itself. So you take the gradient with respect to me, I cannot tell you any information about my neighbor. When this happens, the biggest spectrum happen to be the biggest diagonal entry as well. The second situation is slightly tricky. I think it's more like manipulated. When the Hessian looks like this is essentially saying every coordinate is playing the same role in the objective function. This is essentially x1 plus x2 plus xn squared. So every coordinate essentially is playing the same role. So when you take the gradient with respect to me, I can exactly tell you what is the gradient with respect to my neighbor. So gradient descent is paying actual effort to compute the same redundant information. So of course, gradient descent is more expensive, yes.
So yeah, I'm curious, does your randomized coordinate descent induce more bias?
Okay. What do you mean by bias?
For example, if some of the coordinates are chosen a lot, while the others are not.
Some coordinates are chosen more frequently than the others, yes.
Mm-hmm.
Yeah, we are getting back to that. Yeah.
Okay, thank you. I'm looking forward to it.
Yeah, thank you. Oops. Right. So this is a summary that random coordinate descent always saves, and sometimes it can be defaulted cheaper. And we ask a question: when we incorporate random coordinate descent into Langevin Monte Carlo, can you say the same thing about the saving? So let's take a look. So this is what we had before. The overdamped and underdamped, both of them requires a computation of the gradient. And random coordinate descent is saying that in each iteration, I just randomly pick one coordinate and I say I only compute this coordinate and everybody else get kept the same. And I denote it by capital F. So we just put it in, right? So this is my original formula for overdamped Langevin Monte Carlo. And this is my new formula, random coordinate descent, LMC. Immediately, we encounter difficulties. So we have the gradient get replaced by capital F. Then what do you do with the Brownian motion term? The first thing you can do is keep it as it is. So that's a lazy choice. We gave it a lazy name, random coordinate descent LMC. So when this happens, you take a step back and think what is happening. So the mechanism for random coordinate descent to wane over gradient descent. In each iteration, you randomly pick one coordinate. So on average, if you take d iterations, then everybody sort of get a chance to descend once. But if you keep the Brownian motion as it is, this is essentially saying that in each iteration, you pick one random coordinate to descend, but everybody fluctuate, right? So after d iteration, every coordinate descend once, but everybody oscillate d times. So you're adding a lot of arbitrary, like redundant oscillation in there. So the intuition actually tells you if you do that, this is going to give you a worse performance. We're going back to that later. A quick fix to it is to say in each iteration, I pick one coordinate to descend, and only this particular coordinate gets the oscillation, the Brownian motion, and everybody else keep untouched. So when this happens, we will basically inheriting what random coordinate descent is doing for gradient descent. So we expect the same saving in the sense that the d dependence is the same, but the L dependence, the conditioning dependence get chosen in a better way. So this is the summary. When you do random coordinate descent into LMC, we expect worse result. And when we choose random coordinate to do LMC, we expect similar results as what the random coordinate descent is doing for gradient descent. Okay, so let's justify it. I would like to give you some confidence first. So let's go with choice number 2. So this is to say that each coordinate get oscillate once after d steps and descend only once. So we have exactly the same assumptions. The convexity is mu. The Lipschitz constant gives you the upper bound of the Hessian. The Hessian has the biggest diagonal entry, and we have the upper bound and lower bound of L and L max. The result we have is the following. So in comparison to the classical overdamped Langevin Monte Carlo, which calls for the cost is d squared L squared, the new result that we have when you choose a random coordinate version is d squared, you replace L by L max. Well, they have the summation of blah, 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 and you take the maximum. That's you're replacing L by L max. So this is the same behavior that we were expecting to have. The d dependence is the same, but L dependence get replaced by L max. Therefore, depending on the conditioning of the problem, you may have some saving. This is a reference from 2 years ago. And this paper is kind of a singularity of this whole community in the sense that it has a very special way of proving things, which they reduce the L squared to L. And we haven't seen these techniques used in any other references, and we cannot really follow that technique either. But nevertheless, you can still imagine there are still situations where L max squared is bigger, smaller than L. Okay, so the explicit statement of the theorem is the following. So let's get back to that. So xm is your mth iteration sample, and qm is your probability. In Wessel-2 distance, the probability converges to the target distribution exponentially fast, which is expected up to the discretization error. And this discretization depends on the convexity and the step size, and also depend on the Lipschitz constant per direction, and pi is a probability for ith coordinate to be chosen. And now we have the explicit format of the discretization error, so we can minimize it. If you minimize this error, you find out if pi, the probability of ith coordinate to be chosen, is proportional to this Lipschitz constant, this term is minimized. And accordingly, you can compute the numerical cost for the iteration for the convergence to epsilon. I should mention that the step size is also accordingly adjusted. If a coordinate stiffness is high, L is high, then the probability of this coordinate to be chosen is high. Then associated to that, in each step, when this coordinate gets chosen, the step size has to be small. So on average, everybody march forward at the same time scale. So the step size h is 1 over pi. Yes, please.
So how do you know the value of Li?
Oh, that's a good question. We don't.
Oh, okay.
This is only for theory. Yes.
But the algorithm needs, no? Pi was,
yeah.
how can you actually run the algorithm?
You have to do some sort of estimation or something adaptive to make it practical, I guess.
You make assumption, basically. Yeah.
No, the algorithm needs it.
That's true. So the so a fair comparison is when you do Langevin Monte Carlo, without this Li information, you need your step size to be smaller than 1 over L over there anyway, and you don't know anything about that L, so you make a guess. Yes. So let's move on to overdamped, the underdamped. Underdamped is the same story. We want to replace a gradient by the partial derivative. That is to say, everybody else kept untouched and pick one coordinate to be updated. Conditioned on the previous information, the new update is a Gaussian random variable following the mean and covariance. You can explicitly compute it. And over here, you have the partial derivative. So that's cheaper per iteration. The result is the following. So the underdamped, classical underdamped result has the D dependence being 3/2, and L dependence is also 3/2. So when you do the random coordinate version of the underdamped, the D dependence get kept the same, but L get replaced by L max. So it's the same story because L max is always smaller. You always get a cheaper algorithm, but L sometimes can be D as folded more expensive, D folded big, so you get D folded cheaper. So the exact statement of the theorem is also the same. You have the exponential convergence in terms of the Weissenstein distance, and you have the discretization error. And now, in order to control the discretization error, this pi, the probability of each coordinate get chosen, is Li to 2/3. We don't know why, but this is what we got. So also, if your coordinate is stiff, you get to chosen more frequently, and you have to adjust the step size h accordingly. So we put it on our table. This is exact resemblance of what we have in optimization. In optimization, random coordinate descent wins by when your conditioning of the problem is interesting, and in sampling, we also have the same behavior. So good. So I'd like to remind you that previously we had a bad choice. We believed that when you choose a Gaussian random variable to be a high dimensional random variable, in the sense that in each iteration, one coordinate descend, but everybody oscillate. When that happens, intuitively, we believe it's a worse algorithm. And we would like to see if it's truly a worse algorithm, and if it's truly bad, then what is the mechanism that makes it worse? So the answer is yes, it is bad. And so this is a result from the overdamped to the random coordinate descent overdamped. The D dependence, epsilon dependence didn't change. Similarly, from underdamped to the random coordinate descent underdamped, the D dependence, epsilon dependence is even worse. So you can argue that we to get an upper bound, that's easy, right? You just do a fuzzy job. But you can find the counterexample that shows this random coordinate descent version of underdamped is really just bad. If you move one Gaussian to a different Gaussian, this is the simplest sampling algorithm, the sampling problem that you can imagine. Moving from one Gaussian to another Gaussian, if you follow step by step using the underdamped random coordinate descent version of underdamped, the cost is this much. And this is exactly the same cost as the classical underdamped Langevin Monte Carlo. So there's no way that you can win. And we want to see why it's bad. So in this whole business of sampling, the mechanism or the techniques that we use is a coupling method. So you develop two trajectories. One trajectory, I call it X, that follows the algorithm. And one trajectory, I call it Y, it follows the stochastic differential equation, the Langevin dynamics. And you compare these two trajectories, and you hope these two trajectories contract in some sense. So I call this distance Y and X by delta, and I just expand it out. And I find out that the new iteration delta equals to the old iteration delta with some other terms. And we look at these terms, they can be glued into three categories. This term is a good term. You pull out this mu, and this gives you 1 minus mu h. So this is a contracting term, and you hope to keep it there. And this term essentially comes from discretization. You discretize your Langevin dynamics into smaller chunks. Now, of course, you're paying some discretization error, and this is not our contribution. We just copy paste it from the previous result. So what we need to do is to bound this error. This is the error that you get when you replace the gradient by the random coordinate version of the approximation. So our job is to make sure that this term is going to be somewhat negligible compared to the discretization. And we put it into our chart, and we find out that this error term, when you have the classical Langevin Monte Carlo, of course, this term is 0. But if you replace it by the gradient descent, this is the amount of error that you accumulate. H is the step size, D is the dimensionality. It is much larger than the discretization error that you see. So of course, it brings more error that drives up your cost. And we think a little bit more of this term. So this term is you replace the gradient by the random coordinate version of the gradient. So each time you pick a random coordinate to represent the full thing, on average, you truly represent it, but that introduces a lot of variance. This high variance sounds somewhat similar, and we have experienced it in optimization again. In optimization, especially in stochastic gradient descent, when you're in stochastic gradient descent, the objective function is the summation of a bunch. Therefore, the gradient is the summation of a bunch. So in each iteration, you randomly pick one representative to represent the full gradient. So on average, you represent the real gradient, but this random process gives you the high variance. So there are variation reduction techniques that is to control this variance. One example is Johnson and John. This is to say that once in a while, you compute the true gradient, but in each sub-iterations in between, you just randomly pick one sub-function to update it to get the true gradient there. So we borrow the same idea. We are viewing the gradient as a summation of a bunch of partial derivative, and we say that every once in a while, you compute the true gradient, and in the sub-steps, you just randomly pick one coordinate and update only one particular coordinate. The hope is every once in a while you get the true gradient. So at least for this particular steps, the variance is 0. And in between, you're sort of controlled. So so all these strategies, we just borrow it from Johnson and John, and we find out the mean, of course, is 0, and we need to control the variance. A different strategy is SAGA, stochastic averaging gradient, whatever this A stands for. It also says the same thing. Initially, you had to prepare the true gradient. And in the following steps, in the following step, in each iteration, you just update one. You choose one coordinate to update it, and everybody else you keep the same. You keep the history basically. And we borrow the same technique. So now we inherit this variance reduction technique into the random coordinate descent version of Langevin Monte Carlo. Let's see what will happen to the variance. The variance is reduced. The H dependence is increased. So this is good. This error is comparable to the discretization error. In particular, this is the error that you accumulate per step, and you accumulate a lot of steps. So one H drops out. That basically tells you that this is the number of iteration. 3/2 is the number of iteration you have to pay for epsilon accuracy. So we glue everything together, and this is our final result. For the overdamped case, in terms of the cost, if you just replace the gradient by the partial derivative, the cost is not reduced. However, if you incorporate the variance reduction technique into random coordinate descent LMC, this is your cost. In both D dependence and epsilon dependence, it's improved. The same story can be said for the underdamped. For the underdamped, I particularly want to emphasize this particular term. So this is a term when epsilon very small, this term dominant. And you are basically looking at the cost. The cost of underdamped Langevin Monte Carlo is D square root. Although we cannot show the optimality, but it's very hard to imagine that you can improve. Yeah.
When you use these variance reduction techniques, like at each step, you're using like approximation of the full gradient. So wouldn't the cost of each iteration now scale as du?
Sorry, can you say that again?
Correct me if I'm wrong, but if you use like a variance reduction technique, then at each time you're using an approximation for the full gradient.
Yes.
So does that mean like each iteration now costs d time?
No, you only update one partial derivative.
But when you do the Langevin step, don't you?
Oh, right. So it depends on what you call what do you mean by a cost. So if each coordinate get updated, that's a cost. Then you are right. Then each coordinate get updated. But the problem is, I think to me, computing the partial derivative itself is a cost. So now you're only updating one, so everybody else still kept the same.
Okay, yeah, I agree in terms of like the number of gradient evaluations this saves.
Okay, then, okay.
Thank you.
Yeah, thank you.
Maybe your point is that in SVRG, every now and again, you evaluate a full gradient, right? And then in between, you just evaluate one component. So the ones where you evaluate a full gradient, you should count that as a cost of D. Right?
When you do the Langevin step itself, since you're adding like an approximation of the full gradient, you're actually updating all D coordinates in each step.
Yeah, so that component of the cost, we don't really care that. Yeah. So okay, so I'm really happy with the D square root for the cost. So that's a lot of algorithms. So let me summarize it a little bit. For both overdamped and underdamped Langevin Monte Carlo, you move from the classical Langevin Monte Carlo to the reduced, the random coordinate version of the Langevin Monte Carlo. In terms of the D and epsilon dependence, you do not see any improvement. The improvement can be seen only in the conditioning of the problem, depending on L versus L max. However, if you say that in each iteration, you only update one coordinate and everybody else do not fluctuate, you get the random coordinate descent. Sorry, what I'm saying. So in each iteration, everybody fluctuate, but you only update one coordinate. When that happens, you have the random coordinate version of it, you get the worst result. However, if you incorporate various reduction technique to the worst result, it drags you down to the better performance. So that's a take-home message. It's included in 3 papers. The first paper is about the variance reduction. It's recently accepted, and I highly doubt the reviewer is probably one of us. And the second and third paper are the random coordinate version of the LMC. Thank you very much.
Okay, any questions?
Yeah, so go back to the previous question on the bias. So I'm really wondering what's the h to 0 limit of these randomized coordinate descents? Because so if you think about the original overdamped or underdamped Langevin dynamics, of course it converges, both of them converge exponentially fast, but in some sense you're alternating the dynamics. So when you think about the h go to 0 limit, it's no longer the precise dynamics. So I would guess it induces bias, and also does it still converge exponentially?
Okay, so you're talking about the underdamped, the random coordinate version of the underdamped Langevin dynamics.
Both overdamped Langevin, but the h go to 0 limit, really.
Yeah, so the dynamics, not the algorithm.
Yeah.
Right. So we do not have the exponential convergence, but we can prove it's converged. We don't have the rate.
So why is that happening? So why do we have that they converge exponentially in the discretization level?
Oh, no. Well, I should say that the Langevin dynamics, it converges, but we do not have the technique to prove the convergence rate is exponential.
Yeah, so basically, I think the problem here is if you simply let h go to 0, then definitely this RC/LMC will converge to the right limit. So basically, the overdamped Langevin diffusion equation. So the reason is if you think h is very small, then basically you randomly choose the coordinate, this phenomenon will disappear. And however, I think the right question to ask is, so basically now you let h go to 0, then from some time interval delta t, you use the same you use a random coordinator to update. So basically, you need to add another delta t here into the system. Then you will have a different continuous limit. And in that case, I think we still have the exponential convergence rate, but we don't know the rate. Yeah. Does that answer your question? Okay, cool.
Any other questions? Yeah.
Have you thought about the randomized midpoint discretization?
Yes. No, we haven't been able to figure out anything. But yeah. So that's a very good. Yeah, that's a very good result. We don't know how to use it. Yeah.
Maybe I just have a question. So you said that when you did RCD, where you add noise onto everything, can't you just scale that noise by a factor of d, and then ultimately we'll sort of have the same expected effect as adding noise to a single component? Just divide by d, and I mean, or do you keep that noise parameter the same in RCD as you have for full gradient?
Yeah. We have not thought about it.
Okay.
Yeah.
Wouldn't that every step be of complexity because you're adding something every component?
Yeah, but that's one of the methods she analyzes is it's like that. But I'm saying that the objection that Qin raised to that was that you would be, yeah, okay. Okay. Well, Thank you very much again, Qin, and thanks to all the speakers this afternoon for a great
Thank you.
session.
Thank you.
Okay, so that's all done.